Thank you, Bruce. So let's get the slides going. Yes. So my talk is titled Robotics and Sensors using Erlang. So it's a talk where we're using our GRiSP platform, building embedded systems with Erlang, and interfacing with the real world. My name is Adam Lindberg. I work for Per Stritzinger. As Bruce said, I've been doing a little bit of everything and recently got into embedded hardware, basically, and low-level things, scary low-level things. So this is where I'm at the moment. So the outline will be, I will describe the hardware of the GRiSP itself. We'll talk a bit about what components you can connect to it, what the goal of our kind of interfacing with the sensors and components. I'll show you how the software is structured. So we'll talk about how we get Erlang on this embedded board, how you will develop on it, how we build our drivers, and how you build high-level drivers and applications in Erlang. And then I'll wrap up with some future developments, what we're working on at the moment. And I will sprinkle some demos in between here, so we'll get a bit of fun as well. So in fact, I will try to be as bold and start with a demo. So let's see if this will work. This is a very high resolution. Can I mirror my own display? Okay, this is a little bit better. So what I will show is I will show the GRiSP board, the hardware itself. And what I will do is I will basically start the system. So just remove everything, press the reset button, and watch it boot. So this is what you can see in this window here. I'll make it a bit bigger. So what happens is we boot the bootloader, the low-level stuff. We initialize the hardware. And then you can see here in the middle, we're starting the Erlang runtime. And that one will boot. This is the point where it kind of stops a bit. So what happens is that the Erlang runtime is started, and now it starts to basically load up the VM and load up all the OTP code. So in a short while, we'll see the SASL log start appearing, and then we're actually in real Erlang land. So the reason that this is a bit slow is because we're still working on the SD card performance. So currently, we don't have any direct memory access, therefore reading from the SD card is a bit slow, and Erlang is kind of fighting a bit with the I/O, reading from the card and printing to the serial console. But we are booted. So this is an Erlang shell. We're currently running on some pre-17 version, almost 17, because that's what we had our patches on. The goal is, of course, to move to later versions, and I will talk more about this later in the talk. So this is a normal Erlang shell. Stuff that you're used to will work. So we can start by checking where we are. And we are in our little embedded world where there's not so much on the file system. And actually checking what's in the SD card, you can see that there's some Erlang stuff in there. So the program that's running right now is this beam here. So we're actually running Erlang on this thing. There's no kernel, no nothing. There's Erlang on the bare metal. And to spice things up a bit, we have a GRiSP runtime. So I can do this. This will be a bit slow again because now Erlang goes down to the SD card and tries to like search through the code path everywhere to find the right modules. So soon the SASL output would come. So the GRiSP runtime is basically an Erlang application that runs in this Erlang VM, has a couple of processes and has a couple of drivers that can interface with the GRiSP hardware. So it provides you with a high-level Erlang API to all the hardware, nasty hardware stuff. And it's starting to become quite a few processes because we have some different ports and functionalities. We have drivers for things and for the LEDs and so on. So this is what I will demo now. Maybe I can just put it here for now so you can see the LED there a bit. So This is an example module I'll use. Can everyone see this, or should I bring it a bit higher? Let's do it this. So it's the LED module, nothing fancy. There's 2 RGB LEDs on this, so I'm just gonna set one of them to red. And yes, it works, very nice. And let's do something else. We'll flash the second one blue, for example. That was odd. Didn't expect this. Let's go for a color instead. And this worked, so yeah. This is how basically, our goal is to make this as much Erlang as possible, so you don't have to know all the hardware stuff and can still work with the board. So let's go back to the talk. So first I will talk about the hardware itself, how it works, so the specifications. This is the board, a bigger picture so you can, because you can see the small one up here. And what we call this a embedded wireless device. So the goal is to be able to build embedded applications and use it wirelessly, so we have Wi-Fi on board. The way we achieve this is we're using Erlang, and it's a real Erlang VM, and we're putting this bare metal on this device. So this is like, you'll never get this close to bare metal with Erlang in any other way. I mean, you can get it in a similar way, but this is as close as you get. So I'll explain the whole kind of software side later. So this is the board itself, and we couple this together with connectors for different sensors and actuators, so you can actually interface with the real world. And we want to build lots of drivers for this, so you can build Erlang applications that use all these components. So the specifications themselves, it's a 300 megahertz processor, 64 megabytes of RAM, built-in Wi-Fi, and MicroSD for storage. So I'll explain them all a bit more in detail. So first up, the CPU. So it's in the middle, it's the big one there. It's a ARM Cortex M7 core. It's a 32-bit system on a chip, and it uses the Atmel SAM V71 microcontroller. It runs up to 300 megahertz, so you can scale it. It has a floating point unit built in, and digital signal processing extensions that you also can use. So it's a nice processor, comes with lots of features, and we plan to use as many of them as we can. The RAM sits on the side for storage, and also the micro SD slot, so you can put something on there from your computer. So internally, the CPU has 2 megabytes of flash and 384 kilobytes of SRAM. So this is nowhere near enough to run Erlang. So we put externally, we put this 64 megabyte SD-RAM chip, which is plenty for Erlang. So just looking at this one I had now, it's Erlang VM booted takes about 6 megabytes, something like this. So you have quite a lot of memory, especially for building embedded applications. So you can do some pretty cool stuff on this one. We have EPROM storage for configuration or other things. So this actually survives power outages and reboots and so on. So if you want to store some configuration, that's, for example, if you want to provision devices and then send them out the field, this would be a good place to do it. And of course, the micro SD slot for external storage. So this is where we kind of boot everything. The bootloader goes into the micro SD card, reads an ini file, and then boots whatever you tell it to boot. We have Wi-Fi on chip, and this is a normal BGN Wi-Fi, 2.4 gigahertz band. It's connected via the internal USB interface to the processor, and it's the normal kind of Wi-Fi speed for 2.4 gigahertz, theoretically up to 150 megabytes, usually lower, but yeah, so it's a standard Wi-Fi chip. And it also has a power saving mechanism, so we could also use this to, if you want to hibernate the board, you can bring the Wi-Fi up and down, maybe only at certain points, for example. So now we come to the kind of connectors for more fancy stuff. So this was all pretty basic. It's just a computer, right? What we put on our board that maybe distinguishes is from bigger boards, bigger and cheaper boards like Raspberry Pi and BeagleBone and so on is like all of these connectors that we have. So I'll go through them. We have two generic GPIO ports with 6 pins, so they're up here. And what also is controlled by GPIO is the LEDs on board, so you have 2 RGB LEDs. And we have 5 dip switches, which you can check the state of, and the reset button. So all of this is GPIO, general purpose input-output. And it's kind of generic pins that you can control in runtime. So you can say, okay, I want this much power, or high, low, send kind of ones and zeros on them. And what's neat is that these supports pulse width modulation. So we plan to have drivers where we implement the pulse width modulation for you in the C side, and then you can write Erlang drivers so you can do stuff like LED brightness. So the LEDs I showed you here, for example, the red and blue ones, currently there's no way to set them to like a lower brightness or a nice mix between 2 colors. So you can just light the R, G, and B component. So once we have pulse width modulation, you'll be able to like smoothly transform between all colors in the RGB space. What also you can do with pulse width modulation is you can control motors more precisely. So instead of just blasting at full speed, you can go slowly or faster, accelerate, deaccelerate, and so on. So it's a nice feature to have. And it's used in many other components as well. What's more is that we have a UART port. So this is stands for Universal Asynchronous Receiver Transmitter, and it's asynchronous serial communication, basically. It's generic bit streams, so it's kind of ones and zeros, and you can configure the data format and the transmission speed. So here we're talking about stuff like baud rate and so on. And normally when you talk to UART devices, it actually is it's a text-based protocol most of the time. So it's kind of like you send a command, like a string with some codes or a word and some parameters, and then you listen and this device sends something back, for example. So it's a very simple one. But it's much more high level than GPIO because it's not about controlling pins, ones and zeros. You actually have text, for example. And to go even more advanced, we have 2 SPI ports. So we have one 6-pin port. So all of the ones up here are 6-pin ports. And there's also one SPI port which is 12-pin and has extra pins for interrupt. So you can see it here, like that this one is slightly larger than the other ones. So it has twice the amount of pins. So SPI is a serial peripheral interface, and it's synchronous serial communication. It's a bus. And it is kind of simple like GPIO, but you have this serial aspect of it, and it has very broad support among chip makers. So lots of chips just know how to talk SPI. Lots of other components know that it's a pretty standard protocol. For example, you can have these nice oscillators that can show you like the SPI. You can debug the SPI on the wire, lots of stuff like this. So there are many nice components that know how to talk SPI, and we do as well. It's quite fast protocol, so it's up to 20 megabits per second, megabits per second. And the way it works is that you send and receive at the same time, and that's why it's a synchronous protocol. It's also a master-slave protocol, so it means you have a controller, which in our case will be always the GRiSP. And then you connect lots of components, and then you use what's called a slave select line to actually decide which component you talk to. So you have 2 lines for input-output, and you have one clock line that determines the rate of which you're communicating. So if you hook up, for example, 2 components on the same SPI wire, you use the slave select to decide which one to talk to at the moment, and then you start blasting on the input-output lines, and you can then talk to this component. And the bigger SPI port we have extra interrupt lines. So, for example, some components, they can listen for events, or, for example, the accelerometer can detect free fall and then send you an interrupt, which will end up on the GRiSP side, and then we can do stuff with this in Erlang. For example, generate an event or send a message or something like this. In addition, we have I2C connector. Sits in the middle. So it's a smaller one, and it points straight up, 8 pins. And I2C is inter-integrated circuit. That's why it's called I2C. It's also a master-slave protocol. It has less wires than SPI, so it's only 1 data and clock line plus power and ground. So it's 4 pins instead of 6. What's nice is that it has addressable clients, so you can send like packets of data to a specific client in this bus. So you can chain lots of components, and you can say to this one I want to send this data. And it's usually used for board local stuff, so stuff that sits around your board, because it's unreliable over longer distances. And it's slow compared to SPI, so it's only about 0.4 megabits, so it's much slower, but it's also a little bit nicer in some respects, so it's a nice choice to have. And the last one we have is OneWire, so it's a protocol called Dallas OneWire, and it's developed by Dallas Semiconductors. And what is cool about this one is that it's only 1 wire plus ground, so it's 2, but its data and power goes on the same wire. So when you have devices connected on this, they can charge themselves on the high. So whenever there's a 1 going on the wire, they also charge a capacitor, and then they use this to power themselves over time. So it's a really neat one. And it's similar to I2C, so you have addressable clients and so on, but it supports much longer distances. So we're talking room or house scale, where you can draw like wires. So if you have this one sitting in a corner somewhere, you can pull like temperature sensors around in your house and then get all the data back. And you only need this tiny 1 wire system. So also in this one, it's kind of a MICROLAN. So you have addressable clients. So every device has a 64-bit address. And it's a unique ID plus some device type, so you can actually know which devices you're talking to. And it's very popular for like buttons, like key fobs or weather sensors, stuff like this, because it's low power and kind of nice distance. So for example, you can buy lots of prepackaged like weather sensors that then, like it's a box, nice box, you can put it outside somewhere, and then you have a 1-wire cable, and then you can actually connect it directly to the GRiSP, for example, or some other hub. So for interfacing with the programmer, kind of, or for getting power, we have the MicroUSB connection and also a JTAG debugger, an onboard debugger. So we use the MicroUSB for power, so from my laptop in this case, from battery packs or something like this. It also exposes a serial console and a JTAG debugger access over the USB. So you have 2 USB consoles or 2 USB ports, one for the console and one for the serial console and one for the JTAG debugger. And also we have this external JTAG connector, which is a standard ARM 2x10 pins, where you can connect a hardware JTAG debugger, and you can do cool stuff like actually step the processor, so you can like freeze the whole system. And you don't have to change your software, because it's all of those features are in the processor themselves. So you connect the debugger and you can actually step through your whole system like a step debugger for normal languages, which is pretty neat. So it's useful for developing low-level hardware stuff. So next up, I'll show some examples of what you can connect to this device, and I'm going to focus on something called PMODs. So PMODs are standard by Digilent, and it's small components, 6 or 12 pin ports, and they usually talk one of like SPI, UART, or GPIO, which means you can plug them into all of these ports and use them. So I'll just give some examples of some components that you can buy. Digilent has up to 90, I think, components, and there are other manufacturers following this standard as well, because it's simple. So for example, lots of these chips that are on board, like an accelerometer chip, it's really tiny one. So what Digilent does is they take this, they build it on one of these PMOD boards, and then you can give you a nice interface and you can use it. So many companies who develop their own chips, they also sometimes build PMODs because it's an easy way to test it. So there's lots of PMODs already out there. You can go to electronic stores and find these nice collections of various PMODs, like for robot kits and weather stuff and sensors and all kinds of things. So I'm just going to show a few examples. this one called Con3, and it's a GPIO PMOD that implements a it has 4 standard 3-wire servo motor connectors, so you can connect servo motors to it. This is called PMOD nav, which is a 9-axis inertial measurement unit, which means it has accelerometer, gyroscope, and magnetometer built in. And it's actually 10 or 11 axis because it has a barometer on top where you can get stuff like temperature, air pressure, and so on. So this one is really, really cool. It's a quite new one, but it gives you lots of data. So you plug it in, stick it on a drone, and then you already can have like quite a lot of data to work with. Simpler version of the same idea is just ships which has one of the parts. So this is a gyroscope, for example. So it's a 3-axis gyroscope, works over SPI. And this is a 3-axis accelerometer. And so this new one is the cool one because it has all in one kind of, but you can also buy them separately. And I'm gonna demo this one later. HB3 is a H-bridge driver, so you have feedback inputs. So you can drive a DC motor with up to 12 volts. So you plug in the motor and some external power to this, and you can actually drive a motor. A very similar one is the HP5, but it has a 6-pin JST connector, which is something that these Digilant motor gearboxes uses. So they have you can see it there, they have a little chip on the motor itself, so it's a more like advanced high-level interface. It's the same kind of motor, so it's a 12-volt DC motor, but you can get data from this one. It has a little sensor like how fast it's spinning, where it's rotated at the moment, stuff like this. So it's nicer high level, and you can buy them in kits like this, so you get the motor and the PMOD together. The last one is a example of a UART PMOD, which is a GPS receiver. So this one has like 3-meter 2D satellite position accuracy. So if you have something out in the wild, you could theory use this to figure out where you are. So these are just some examples of PMODs that you can buy already and connect, and the prices vary between $5 up to $30, $40, depending on how advanced it is or what you want to do with it. So I'm gonna do another demo. So I'm gonna use just the board, but I'm gonna connect a PMOD to it. So I brought with me the PMOD ACL2, so it's the accelerometer one. And I'm just gonna plug it in. So in this case, I don't need to reboot because I didn't talk to this. And if you just plug it in, like the pins are in some normal power state, so it doesn't mess with anything. So actually, I don't have to reboot. Now that I install this, I can just leave it here. And I will show you how this looks like. Nice flickering, and we are back to our Erlang shell. So I told you that we had a GRiSP runtime. So as you can see before, as I showed you before, we started the GRiSP application, and this started some low-level drivers like SPI to talk with SPI components and other things. So I'm going to stop this one. So now the runtime is stopped, basically. The hardware doesn't really care, but the runtime shut down everything. And I'm going to tell the GRiSP application that we have some devices connected. So the way this works is that you could either configure in your sysconfig or like this dynamically, or maybe we add some API for like pulling and plugging devices later. But this is equivalent. So we'd say that on the port, the SPI port 1, which is this one, which is the extended one, we now have something connected. And this is a PMOD ACL2. So that tells the GRiSP runtime to, when it boots, it also starts a driver instance for, okay, I misspelled. So let's do it again. The reason I'm doing it again and not just fixing the line is because the terminal emulator we're using is a bit stupid. So it doesn't have proper line editing. So this is just using the serial interface over the USB. And you could use Screen, for example, to connect to it. We're using a OS X app called Serial, this one, because it has some other nice features like line editing mode and so on. But it's up to you how to connect to this one. So we told GRiSP about this, and we're now going to start GRiSP again, the runtime. And what we can see here in a while after all the basic stuff started is that also this pmod ACL2 driver has started. So because this one has started and it knows which port, I told it which ports this pmod sits on, you can now use this module, and let's call this function first. Oh, there's some values there. So you can see that I didn't specify like which port I wanted to be on, or the device type is specified by which driver I'm using. So the idea here is that by default, you probably normally only have one device connected. So it's nice not to have to type the slot all the time. So it's actually automatically mapped in the GRiSP application. It knows where your devices are connected and will redirect the drivers to the right device. Of course, you can talk to a specific one if you really want to, if you have like two of the same connected. So this is not a problem. So this is accelerometer data. This is the raw values that comes out of the device. And you can convert them to g-forces. So if I just lie it super flat like this, you can see that the first component is about, the third component, the z-axis is about 1000 and the others are about 0 to 100. So if we actually interpret this as g-forces, which is another feature of the driver, you can see that the x, y, z values kind of look okay because we're lying flat on a surface, so we're in 1G environment here on this planet, and this is kind of normal. So they might need some calibration, but in general this is fine. So if I flip it upside down and I do the same thing, you can see now that we're minus 1G, so you actually can see which direction you are. And if I shake it a bit, you see I get different values on all the axes. By default, it's in a 2G mode. So this one has up to, I think, 8 Gs, and the pmod nav, the cool one, has up to 16 Gs force detection. But the accelerometers themselves, they actually handle much more because it's a electromechanical sensor. So they, I think in the specification it says that it can handle up to 5000 G without breaking. So I'm not sure I'm going to be strong enough to test it, but I'm at least strong enough to produce 2G, which is nice. So I have a small demo where I connect this one to the LEDs. So I will start this. And I'm just going to check what I call the start function. Run, apparently. So it's running. So let's start in this one. So when I hold it like this, you can see that the LEDs are red. And if I turn it like this, they become green. And if I turn it like this, they become red again. So that means I've tied the red component to the, whatever, one of the axes. My spatial awareness is not the best today. And the green component is to one of the axes, and I don't know if you can see it, but it's blue now, basically. And if you tilt it a little bit, you get the combination of the colors. So now you get green and blue, and yeah, a bit different ones. So this is a nice demo where you show actually I built an application, right? I built a program that takes one of the sensors and does something cool with it. So later you could send it to something like if you have this with a battery pack stuck to your, I don't know, your kid's bicycle, for example, and they fall over, you can get like an alarm in your mobile phone or something. I don't know, whatever. So this shows how you actually can connect different parts of the hardware and do something cool. So back to the slides. So I'm going to talk a bit about the software side of things. So far I only talked about the hardware, what you can do with it, what can connect to it. So on the software side of things, we have stuff like toolchain, the operating system, I put quotes around that because I'll explain it later, and the GRiSP runtime, which I already talked a little bit about. So to make all this possible, we're using something called RTEMS, which stands for Real-Time Executive for Multiprocessor Systems. and it is a real-time operating system. But you can kind of see the concept as operating system as a library, because it's not an operating system. It's not managing other processes and like taking care of resources, but it's something that you link into a program. So that's why it's called real-time executive, because in the end you get just one program. So if you write a C program and you link in RTEMS, you get still your C program with lots of libraries behind it. And then you can actually boot from this program directly on the processor. And this is what we're doing with the Erlang VM. It does support standards like POSIX, so operating system APIs. And this is why for us it's perfect, because Erlang uses POSIX, so we can just combine RTEMS, and whenever Erlang makes a syscall or a POSIX call, RTEMS implements this for us. It's very performant, so it's very scalable, like timer, timeout support, uses fine-grained locking for implementing threads and so on. And processes do exist, so you can run actually other programs on this, but they are simulated as threads. So in the end, what RTEMS does, it starts and it takes up the whole memory and it runs alone, right? Which in our case is Beam together with RTEMS. And then if you run a external program, it's simulated by spawning a thread and then managing that memory for you. So you can get kind of neat high-level stuff, or stuff that looks like high-level things in any case. It has SMP support, which is nice because Erlang supports SMP, and if we go for a multi-core processor, we could use this, so that's very nice. And it supports different networking stack, but among other, it supports the FreeBSD networking stack, which means you can compile RTEMS together with the drivers from FreeBSD, so you can get things like Ethernet, Wi-Fi, USB, things like this. And that means that we get lots of drivers for free, and they're fairly advanced high-level drivers, so you can do a lot with them, and it's a nice fit for Erlang, which is also a high-level language. So what we do is we compile Beam together with RTEMS, with the headers and libraries that is RTEMS, and that means we can start the virtual machine directly from the bootloader. So in the bootloader, there is a small config, or in the SD card, there is a small config file that specifies an executable, and there we just say beam.bin. So the way we do this is when you compile Beam, we cross-compile it to the RTEMS architecture, to the ARM architecture, and so then you get an ELF executable, and then we take that ELF executable and we use the object copy tool, which actually converts it to machine code, and then we stick this on the SD card. So basically what's read from the SD card is directly the in-memory code for the Beam, and it just piped into memory and booted, and we're good to go. And all the APIs that Beam needs to do things is provided by RTEMS. So whenever you make call a system API in Erlang, or under the hood in the Erlang VM, RTEMS takes over, implements the thing, and then returns a value. So the Beam doesn't really know that it's running as the kernel, but it is effectively the kernel in this system. So to kind of sum it up, you have hardware, and you compile the Beam and RTEMS together into one big thing. And the Beam does stuff like run OTP and have the GRiSP runtime running in our case, and it runs your application, right? And then RTEMS is like a small middle layer underneath in the same executable that implements all the OS layer stuff. So the GRiSP runtime, it's just an Erlang application. It's a couple of LinkedIn drivers as well to talk with the hardware. So for example, when we need to talk GPIO, so one of the GPIO ports, or for example, check the switches or modify the LEDs, we use a driver for this. And we have a driver to talk to SPI. So we have a C-level layer provided by RTEMS and by the implementers of the hardware board, which interfaces with the SPI protocol. And we then have bindings for this to Erlang, so you can send and receive SPI commands. And this is, for example, how the accelerometer driver is implemented. And then we have high-level drivers for using the LEDs, which I showed you, for reading the dip switches, and for interfacing with PMODs. So we're trying to write more and more PMOD drivers. So the hope is that for at least the most common useful PMODs, we already have ready-made Erlang drivers that you can build Erlang application with. I'll show you a example of how the SPI driver kind of works from C to Erlang, so you get a feeling for kind of what's involved here. So the SPI driver in this case, this is an Erlang port driver, and when we get a message from Erlang or a call, a command from the Erlang side, I'll show you the Erlang code later, we get this binary buffer in here. This is normally how we interface with the port drivers in Erlang. You can decode it as Erlang terms, but we went the other way and said, okay, let's just do all the advanced stuff on the Erlang side because it's much more comfortable. And then on the C side, we just deal with binaries. So this interface is pretty simple. It's a buffer of characters, and the first character in this buffer is the ship select. So this is a number specifying which of the two SPI ports we should enable in this driver. And then the rest of the buffer is just the message we want to send to the device. So later in the code, we create a message struct, and we use this IOCTL function with the file descriptor for the SPI port and the message we want to send. And then from that point on, like, it's the low-level routines that take over the SPI implementation and whatever support for anything like in the CPU and so, depending on what protocols you use. And then we just check the reply and we output, whoops, sorry for that. We send the reply back to the Erlang side. So in the Erlang side, it's pretty simple. It's a driver, so it's a port driver. We spawn it. We want to talk with binaries back and forth because it's nice in Erlang. You can do stuff like send hexadecimals very easily and so on. Here on the Erlang side, we do the mapping. So we map from the atom GPIO1, for example, to the actual, this should be SPI, to the actual index of the ship select that the CPU wants or knows about. Sorry for that. And then we send off this command to the port, and that's it. So an example of how we use this is, I think this is for the accelerometer that I just showed you. So a command in SPI is a couple of bytes. It's usually bytes. So in this case, we send 2 bytes. The first byte for the accelerometer, this is all in the documentation for this accelerometer chip, and you can read lots about which commands and which registers to read and write. So this means read from a register, and I want to read from this register. And I think in this case it's the who am I register, which is like the device ID of the PMod. And we pack this with an extra byte. So the way SPI works is that it's synchronous. So it's one output and one input line. So from the master it's one output, and then from the slave it's one output back. And what happens is they all go in lockstep with this clock line on the side that dictates the speed. And every time you send 1 byte to the slave sends 1 byte back to the master. So this is what means with synchronous kind of. So we're sending 2 bytes, the command and the register we want to read, and we'll get, actually for each of those, we'll get 1 byte back. But we also want the value of the register. So if the value of the register would come in the second byte, the PMod wouldn't know which register we wanted to read because that's the byte that's currently in transit, right? So we have to wait for a third exchange where actually the value comes. And that's why we pad with 0, because we have nothing more to say to the PMod, and we're just waiting for 1 more byte from the other side. And if I send this, I send it as a message to the port, and then I just flush to see what I got back, and you can see that we got some data back. So in the end, we sent 3 bytes, and we got 3 bytes back. And I was nice enough to send nothing in the third one, because I'm not really caring about this. And the PMod was nice enough to send nothing in the first 2, where my command bytes were shipped over, because they wouldn't know what to send there, right? And then as the last byte, I get the value back from this register I was asking for. So this is all very, very low level, but we also implement, of course, Erlang APIs to do this a bit more efficiently. So this is an example of the same call, where instead we're saying, okay, I want to talk on SPI1, I want to send this command, please strip away the first 2 bytes and give me the 1 byte back. And this will handle all the padding and cutting of stuff, so you don't have to think about this. So this is what we use when we implement the PMod drivers, for example. So I'm going to do one last demo, and it's going to be a robot. and I have no idea how it will go. So let's see if we can make this work. So I have another GRiSP board down here, and it has a battery pack, and it's built on top of, screwed on top of a robot, and I have a small program waiting on there, so when I flip a switch, it will try to do some things, and we'll see how it goes. So I will do it this way. Let's see. So you can either come up on the side if you want. I will also try to film it and show it on the screen, so for the people who are back, or for the video. So if you're in front of the camera, please try to sit down in any case, just so you don't block the view. So let's do like this. So I'm going to be very antisocial, and I'm going to call myself. Yay, this is meta. So Bruce, if you would be nice enough to basically just film the robot, so in case people don't see it, or for the future, for internet. So maybe if you stand over here. So it's a small program that pauses for a little while, and then it moves a little bit, and then it's supposed to drive in a circle. And the problem with getting this working is, first, it's all hard-coded, like how much it should turn and drive, so I'm not sure exactly how well it will work. And also getting enough power to the motors with the battery pack was a bit problematic. So we'll see how much energy it has to do something. Maybe it's lazy. So this blue blinking light here means that we're in a state where the program has booted, the GRiSP runtime is running, and we're just waiting for this switch to flip, which I programmed. And once I do this, it switches to green, so now it knows it should do something, and then hopefully it should start doing it. Let's see. And I have some sleeps in between, so. So it looks around a bit, and I'm just going to reposition it, because then it drives ahead. Yeah. And that's it. So this is the GRiSP board here. This is a big USB battery pack. Underneath there is a battery pack for the motors. And if I flip it around, you can see the motors themselves and the two PMODs that drive the motors. So the PMODs are connected with extension cables, the gray ones that disappear under here, to the GRiSP board. And then there comes external power to the motor from the battery packs. And this is it, actually. So I had a hope that we would be able to have the Wi-Fi fully working to actually drive it remotely, but we didn't have time for this, so now it's just kind of hard-coded demo. So let's see. Thank you. So the last part is basically, yeah, what are we working on right now? So I'm going to talk about some issues and the future roadmap, basically. So in terms of issues, we're working on getting full Wi-Fi support. So we have Wi-Fi running, but we have very high packet loss because of some driver issues and some USB issues. So we've been working a lot on this, and it's getting better, but we weren't sure if it would be stable enough for a demo, so we skipped showing it off in this case. But for example, if you boot the board with the beam with the Wi-Fi enabled, you will connect to like the first open Wi-Fi that exists and get an IP number, and then you can actually ping the GRiSP. So once this all kind of works, you'll be able to connect distributed Erlang to it, or even access the serial console over Wi-Fi, things like this. So this will be really cool. As I mentioned before, we're also working on getting the MicroSD speeds up, because we're not using DMA yet, and we just have to do it. So it's on our to-do list. And we have one more problem where the clock speed is a bit off. So I didn't really expose the problem here, but if you do a timer sleep, for example, it takes about twice real time. So we did lots of timer testing with low-level stuff with C programs, and everything is just fine. But somehow the way Erlang uses the operating system timer and clock functions create some problem that we haven't really figured out yet. So currently Erlang thinks times are going like twice as slow. And another funny thing is if you boot it, the time is set to like 0 or something, so it's always 1988. So this is a really retro board from the 80s, which is super slow at the moment. But it's all stuff we're working on. Another thing we're doing is we're part of an EU project called LightCone, which is about Internet of Things stuff, computing at the edge. So in huge networks like internet and so on. And they use things like synchronization-free programming, hybrid gossip protocols. So we're part of this, and we want to use the GRiSP to like as an edge node basically. And because we have Erlang, which is a fairly high-level language, we can still do cool things like use all these CRDT data types and so on the GRiSP itself. So this will be really cool. And the future roadmap for the GRiSP project itself is to get up to speed with the latest Erlang, and we'll probably just go straight for 20 because it's released soon. This means in practice porting all our patches over that we have for this current version and just modernize the whole thing basically. We want to build and improve the rebar tooling we have. So the idea is that like, you know, with rebar 3, you can do rebar 3 new app, something like this, and we want to basically make the equivalent of new GRiSP app, which will set up all your dependencies, give you some nice rebar targets for compiling and deploying onto the SD card. And for real advanced things, we want to do stuff like you can compile your own Beam instance and copy in your own drivers if you want to write really low-level stuff on this one as well. And we'll want to work more on more PMOD drivers and the Wi-Fi and setting all that up so you can use distributed Erlang. So this is it. Thank you very much. So, yes, sorry, I didn't have a slide for this. So I will just explain it with words. We have a raffle going on. I can actually show you the web page. So it means up until Sunday, I think. Yeah, so if you sign up for the newsletter, the GRiSP newsletter, until Sunday, you'll be part in a raffle for 3 GRiSP boards when they finally are released. So I will just show you the web page so you know where to go. So it's grisp.org. This is the homepage of the GRiSP project. And in the bottom, you have the subscribe to GRiSP newsletters. So if you do this before Sunday, you will be taking part in a raffle of 3 boards for this conference. So, any questions?
Yeah. Sorry, my phone is ringing. No, off. So when writing drivers in a normal OS kernel, you often rely on interrupts and the DMA.
Yes.
Is there a way you can expose that functionality to Erlang code level?
Yes, so we plan to do this because, I mean, even like the components like the accelerometers and things, they have interrupts, so we have to get back to Erlang somehow. Right now we're doing everything with port drivers, so you could do it there, but since we got a bit inspired by the OTP talk yesterday, we thought we could use this new NIF functionality and actually do interrupts on the C side and then send Erlang messages back. So this is all kind of in the pipeline to get this working.
Okay.
More questions?
How much patching does Erlang actually need?
Not so much. So mostly we patched makefiles, and this is to first get the cross-compilation going and then get our own drivers into. So what we did at the moment is we put our own drivers into the emulators driver folder, and we add them to a makefile, and we just compile everything in one go. So that's kind of the majority of patches. There are some other generic things that I can't figure out at the top of my head, but like really tiny stuff, like one line here and there, that we probably will push back to OTP because it's just common sense stuff that just haven't been tested in the way we did it. So I would say in average, like very little patching required. More questions? Yeah, when will it ship? Per.
End of July is at the moment, so we hope to verify the hardware.
So I asked the question, when will it ship?
and I'm answering it myself. So the plan is to have by the middle of June have the hardware finally verified when we basically got all the Wi-Fi stuff in order, and we have 6 weeks production run. So the first ports will ship end of July. So we'll be again a little bit delayed. It's on the website.
Yeah, it's on the website, and let's see what the actual. Where's the pre-order button?
Pre-order now.
There, yes.
Buy one.
I block all the scripts all the time, so that's why it doesn't work. So this is the single board, and yeah, with SD card we have a normal one without, and then you can actually get a 10-pack as well if you want for your company or for education. We want to give away bitboards or discount them for education, but if you need a bigger one to try out bigger experiments, we also have a 10-card bundle. Yes. Any other questions?
I have one question, and that's what does GRiSP stand for?
Per. It's a really cool name. Yeah.
It actually stood for a programming language I developed like 15 years ago, and then I learned about Erlang and killed it off, so I had the name left over and the logo, and I reused it. That's that's the truth.
Yeah. Any more questions, or should we wrap this up? 3, 2, 1. Okay, thank you.